In problem 31 here, rather I should say exercise, 31, I am meant to find the absolute maxima and minima of a particular function, once again a second order polynomial, this time with a domain that is not the natural domain of this algebraic expression. Rather, the domain is a closed triangular region bounded by the solution sets to x equals 0, or y is equal to 2, or y is equal to 2x. Well, I began by saying that that function achieves its absolute extrema either on the boundary of its domain or where its gradient is 0, 0. And the gradient of that function is 0, 0, where the system of equations is satisfied. That's a rather simple system of equations. I was able to do some easy rearrangement and get that simplified system of equations and say the solution is, the one and only solution is 1, 2. Solution set only contains one thing. So f has either a local maximum or a local minimum or a saddle point there, so I examined the second derivative with respect to x and the discriminant here, and that told me that I had a local maximum since I was both concave up in the x direction and concave up in the y direction. Next, I need to examine the behavior of this function on the boundary, so I was going to draw the domain. Now, let's see. The domain is bounded by the solution set to x is equal to 0. That would be this line right here in blue. The solution set to y is equal to 2. That's maybe something like this. And y is equal to 2x. So about like that. And let me think about what this point is. Y is equal to 2x, and that is y is 2. So let's see, at what x value would y be 1? And this, this is 1, and this is 2, so this is the point 1, 2. Ah, interesting. So the place where the gradient was 0, 0 is the point 1, 2 right here on the edge. Okay. So that's strange, right? Because actually, if the function is only defined on this triangle, one could ask, does it even have a gradient there? Are derivatives defined on the ends of boundaries? Well, you can only do a one-sided limit on the end of a boundary. So that's debatable, but I will proceed. Now, first of all, I would like to think about the behavior of this function along the line x is 0. So f of 0 comma y, that looks like this. So that term disappears, that term disappears, and y squared is still there, minus 4y plus 1. So I would like to find where this function achieves, this function of one variable achieves its maxima or minima. And to do that, so I'm sorry, let me try to go a little bit faster. Achieves its maximum. Oh, I should say extremum. Where, and if we had a function of one variable, we would take its derivative and set it to 0. So 2y minus 4 is equal to 0. And that is the same thing as saying y is 2. Ah, okay. So, i.e., at the point something 2 and 0, 2. Right? Because we're looking along the line x is equal to 0. Okay. Next, let's take this line. Y is equal to 2. So far. Oh, and let's see. I also need to say and f of 0, 2 is equal to, well, let's think about it. 2 squared minus 4 times 2. So that's 4 minus 4 times 2. So that's negative 4 plus 1 is negative 3. Okay, that could be a local, that could be a global maximum, it could be a global minimum, or it could be neither. Okay. Now we also want to examine the line y is equal to 2, and f of x2, which is, I'm worried that this is not going to fit on the page. So f of x2, where y is equal to 2, along this line, is equal to 2x squared minus 4x, and then let's see, with y being 2, we'd have a 4 minus 4 times 2, so that's negative 4, plus 1, and that is negative 3. And let's see, achieves its extrema, where its derivative, that's a function of one variable, so 4x minus 4 is equal to 0, which means that x is 1. So we should say, and f of, let's see, we want 1, and then what does y need to be? 2, is equal to, hey, didn't we already do that? It's 11. So, okay, we are finding that our function, the biggest it is along this line is right there. The biggest it is along this line is right there. And we have one more line to check. Perhaps somewhere in the middle of this line, the function is the biggest it ever is. So we need to say f of, and we're looking along this line, y is equal to 2x, so we'll say x and replace y with 2x. And what can we get out of that? So we'll have 2x squareds, and over here we'll have 4x squared, so that's 6x squareds in total. And minus 4x's minus 4 times 2x, so minus 4 minus 8, that is minus 12x, and then we have our plus 1 term. Achieves its maximum, or extremum, is extremized, where 12x minus 12 is equal to 0, and that says that x is equal to 1. Okay. Now let's see. What do I have to do? I have to go to a new page. I can't believe it. This is the first time in any video where I've had to go to a new page. Let's see. Maybe I'll do it like this. And I'll start writing big just to spoil myself. F of 1, and let's see, along the line, if we're going to have x be 1, then we're along the line y is equal to 2x, this must be 2, is equal to 11. Okay. The largest value of x, value of f is, then let's see, what did we find? We found 11 11 and negative 3. Yeah, so we need to compare those. We found the largest value of this is we should also check 0, 0. Okay, let's see. F of 1, 2 is 11, and the smallest, 11, is F of 0, 2 is equal to negative 3. Okay, now to recap, we only needed to compare f of 1, 2, which we were looking at for two reasons. One, it was a place where the gradient was equal to the 0 vector. And we also found that it was a place along a line where a function was minimized. Okay? And then we also needed to look at f of 0, 2, because we found that that was along a line, a place where a function was extremized, and 0, 2 is negative 3. Now we should also have looked at the origin right here, 0, 0. And f of 0, 0, going all the way back to the definition of the function here. Let's see, if I put in 0, 0, I'd get 1. And so the biggest of these is 11, the smallest is negative 3, and the biggest is 1. Sorry, the middle is 1. So this is not a global maximum or a global minimum. It's somewhere in between the global maximum and the global minimum. Okay, so I should have said that the absolute maximum, let's see, absolute maximum of f is f of 1, 2, which is 11, and the absolute minimum is f of 0, 2, which is negative 3.